Okay, awesome. Well, thank you so much to everyone for being here. And in particular, thank you to the Pappalardo family for this opportunity and making it possible to be here at MIT. I think it's a really unique experience to get to have so much flexibility as a postdoc in what you pursue and to do that here with all the other amazing scientists at MIT. So thank you to Neil and Jane for making this possible. So yeah, I'm Gillian Kopp, and I will be talking about my research using low-level detector information as a window into new physics. So I'm a particle physicist, and most of this talk will be focused on some of the smallest structures in the universe that we understand. But let's take a step back and look at some of the largest structures in the universe to start with. So this is an example of a classic spiral galaxy. And observations of galaxies like these in the 1970s by Vera Rubin revealed some rather surprising facts. In particular, when you plot the rotational velocities of stars in these spiral galaxies, as you go further away from the galactic center, the velocities end up getting faster. So we see this top curve where we have observations from starlight and hydrogen gas, seeing that the velocities are increasing as we go further from the galactic center. And this differs quite a bit from what we would expect given the visible distribution of matter in the galaxy and its gravitational interactions. We would actually instead predict this lower curve, where the velocities would drop off as we go further out in the galaxy. So this really indicates the presence of something massive interacting gravitationally, and yet that does not reflect light. And we've come to call this dark matter. From early universe observations, from measurements of the cosmic microwave background, we know that dark matter is about 5 times more prevalent in the universe than visible matter. So visible matter only makes up 5% of the energy density of the universe, so everything that we can see and interact with, while dark matter actually makes up 26% of the energy density of the universe. The remaining is made up by dark energy. But this 26% of dark matter, we don't have a great sense of what its nature is. What does it look like in perhaps particle form? The visible matter is very well described by the standard model of particle physics. So the standard model of particle physics really brings together all of the observations in high energy physics, and it's been created over the last century. And this model, I'd like to emphasize, is a massive success. It's agreed with experimental observation to a huge degree, something like 1 in 10 to the 12th for quantum electrodynamics. And it describes all of the known elementary particles, as you can see here, and 3 of the 4 fundamental forces. So while the standard model is a huge success, there's multiple remaining questions. There's the matter-antimatter asymmetry. So in the world around us, we see much more matter than antimatter. And this also comes from the early universe. Some imbalance created more matter than antimatter, and yet in the standard model, that effectively treats matter and antimatter particles the same, so not explaining this imbalance that we have. The standard model also has neutrinos, but does not give an explanation for neutrino mass. And for observations of solar neutrinos and neutrino oscillations, we know that they must have mass. And finally, as I alluded to earlier, there's the question of dark matter. None of the particles within the standard model are a viable dark matter candidate. So we might start thinking about what could be beyond the standard model. And we've come to call this the dark sector. So we have our standard model that we have discovered and has agreed with the observations to incredible precision. But now we're postulating there has to be something else, this dark sector that could contain dark matter candidates. And it could be just as richly interacting as the standard model, having many particles, forces, etc. However, if we were to be able to observe this, to discover this, we'd basically need some way to communicate between the standard model sector and this dark sector. So in particle physics terms, we would call this a mediator, some particle that interacts both in the standard model and in the dark sector, allowing us sort of a portal to see into this new world. And the Higgs boson, which is in the center of the standard model here, is sort of the crowning achievement of the standard model, and ends up being a really good candidate to potentially connect to the dark sector. The Higgs was actually originally postulated in 1964, the same year that Neil graduated here from MIT here, but was actually only discovered in 2012 by 2 of the experiments at the Large Hadron Collider. And a lot of its properties mean that it could still have some sort of open decays that could be a window into this dark sector. So in particular, interactions between the Higgs boson and the dark sector could be accessible at particle colliders. Particle colliders are the only place in the world where we can produce Higgs boson in such massive quantities and also observe their decays to such high precision that we can really start probing exotic decays of the Higgs boson and potentially detect signatures of this dark sector. So here we're postulating that the Higgs is sort of what allows us to communicate between the standard model and this dark sector. And in particular, what we'd be looking for is we'd have a proton-proton collision, producing a Higgs boson, then decaying to two dark sector particles. These would then decay back into standard model particles because that's what we're able to actually observe in our detectors. And what I'd like to emphasize is that we expect the coupling or the interaction between the Higgs boson and these dark sector particles to be quite weak because we expect this to be a rare process. Otherwise, hopefully, we would have observed it already. Because that coupling is so weak, these dark sector particles may have a long lifetime. The lifetime is inversely proportional to the coupling. And by long lifetime, I simply mean that these would be able to last for a macroscopic amount of time before decaying into something else. It might not sound like very long, because this could be something on the order of, say, 5, 6 plus nanoseconds, so very fast in what we typically think of. But on the scales of a particle collider, this actually allows these particles to travel a macroscopic distance, perhaps even up to a few meters, before decaying back into these standard model particles. So this is really what we can start to probe, and these long lifetimes should not actually come as a huge surprise, because this shows particles within the standard model, showing their masses and then showing their lifetimes. The lifetimes are somewhat uniquely reported in meters here. So we actually take the proper lifetime, tau, multiply it by the speed of light, which gives us a distance, and this gives us an example of how far in the particle rest frame that particle would be able to travel before decaying. So just to highlight some examples here, at the bottom we have our prompt particles, which are basically produced and then nearly instantaneously decay into other particles. So for instance, we have the Higgs boson right here. So this would be produced and then would decay into, say, B quarks or into photons. In the middle, we have our muon. The muon has a lifetime of 2.2 microseconds before it decays. And then at the other far end of the spectrum, at the very top, we have the proton, which is effectively stable as far as we know, so basically off the scale here. So there's a huge range, many orders of magnitude, that standard model particles span, and we would expect dark sector particles could be many places along this, and we should make sure that in searching for them, we are sensitive to some of the unique decays they could have, especially if they're long-lived. And the way that we do so, the laboratory that we have on Earth to investigate this is the Large Hadron Collider. So this is the highest energy proton-proton collider in the world, and it's located outside of Geneva, Switzerland, basically on the border of France and Switzerland. So from this aerial picture, you can see the Alps in the background. We have Lake Geneva here, and then this ring is the 27-kilometer circumference ring that the Large Hadron Collider is. It's actually located 100 meters underground, where we have a tunnel dug, and then we have protons circulating at nearly the speed of light, both in counterclockwise and the clockwise direction. Then we take those beams of protons and we collide them in basically head-on collisions at 4 points around the ring. So over here, where the CERN central site is, we have the Atlas detector. And on the opposite side of the ring, sort of in the French countryside over here, we have the CMS, or the compact muon solenoid detector. And this is the experiment that I work on. We also have the ELISE detector and the LHCb detector, which many other colleagues here at MIT work on. So the CMS detector is really effectively acting as a giant camera to record these collisions. Proton-proton collisions are occurring in the center of this detector, and then we use all of the subdetector systems to gain as much information, capture as much out of that collision, and determine what particles it resulted in. Just to give a sense of scale of this experiment, it is a huge detector. It is 15 meters tall and about 21 meters long. You can see the opened up detector behind me in the picture here. So this is sort of the barrel section of the detector. We're typically taking data for about 8 months a year, but then we have an end of year shutdown where there can be some upgrades, and if you're lucky during that time, you can get to go down into the experimental cavern and actually see the detector that you're working with for the whole year. So behind me is the opened up section of the barrel, and basically we use multiple portions of this detector to gain different information. So again, here's sort of a cross section. If you think about the proton beams, they'd be coming into and out of the page and colliding in the center of the detector. The first layer that we have here is the tracker. This is primarily made of silicon, and it's designed to detect the paths of charged particles. Outside of this, we have the first layer of our calorimeter system. Calorimeter simply means we're performing energy measurements. And the first layer is the electromagnetic calorimeter, or ECAL. So this detects the energies of photons and electrons. Outside of this, we have the second layer of our calorimeter system, the Hadron Collider. This detects composite particles, such as neutrons, and it's called the HCal. And I spent quite a lot of my time working on the HCal. I am co-convener of the HCal Detector Performance Group, so a lot of my goals here are making sure that we give the best energy measurements and the most accurate timing alignment such that we're providing the most accurate physics measurements for the rest of the experiment. And working on this detector really emphasizes how much of this experiment is truly a marvel of engineering. The number of people and of groups that it takes to make this entire experiment work, to give accurate measurements, the number of experts who are on call in the middle of the night when something breaks is truly astounding. Outside of the HCal, we have the superconducting solenoid. So this is a very strong magnet giving a field of about 4 Tesla, which is helpful because that means that we can curve the paths of charged particles in order to identify positively versus negatively charged particles. And outside of this last section that you see are the muon chambers. So muons will tend to travel through our inner detectors without depositing much energy in them, and most of their energy will be deposited in the muon chambers that we'll detect. One item of this picture that is often not discussed are the cables. So over here, you can see these cable systems, and that's how we end up reading the raw information off of the detector and starting our data processing chain. This raw detector information gives us a huge amount of access to detailed information that is often not propagated downstream. And this information can really help us distinguish some of our signatures of potential dark sector physics as compared to standard model physics. So for instance, if we go back to thinking about that dark sector model, where we postulated that that particle might be able to live for a few nanoseconds, thus traveling a few meters and then decay, we'd get the signature of a displaced jet. So displaced jet, a jet is basically a collimated shower of energetic particles, all really contained in this cone. So over here we have in blue this displaced jet, where its origin is actually not at the particle collision point, but a few meters from that. And that contrasts quite a bit with what we expect from a lot of our standard model processes, where we have a prompt jet. In orange, where you can see that traces back directly to our collision point. And the low-level detector information that we have can really help to distinguish the two of these. So in a prompt jet, we'd expect to see many tracks and then hits evenly distributed in our calorimeter system. In contrast, in a displaced jet, that may be entirely trackless because the particle would travel through our tracker without depositing any energy and being recorded there. And then once we get to our calorimeter system, we could have this dense cluster of calorimeter hits that is not nearly as widely spread. So information about the timing of pulses and the spatial granularity of these energy deposits that we can access at this first level of our data acquisition system can really be a window into this new physics. And this is a sort of limitation that I recognized because in CMS, we're colliding particles every 25 nanoseconds. So that's an event rate of 40 megahertz. We simply are not able to save all of that data for offline analysis. That's just more hard drives than we have and more data that we can analyze offline. So the way that we handle this is to have a 2-tiered trigger system. The first level is done completely in hardware, making really fast decisions about what information we should save for offline analysis. The second level is done entirely in software. So you have a little bit more time, a little bit more information to make those decisions. But at the end of the day, that means that we're only saving 1 in 40,000 events that were taken by CMS. And if we don't save those potential dark sector signatures in our trigger system, there's no way we can recover them offline. So I recognized this and implemented a displaced jet trigger at the first level, at the hardware level of our trigger system, focused on using some of the HCal information. That's been running for the last couple of years and has really allowed us increased sensitivity to these long-lived particle models. So again, going back to our thought of we might have this displaced jet, this shows the trigger efficiency versus the particle decay position, showing that we have sensitivity over 90% to particles that are decaying between 2 and 3 meters from our collision point. And 2 and 3 meters corresponds exactly to the inner and outer radiuses of the HCal. So this is using information about the spatial granularity of energy deposits in order to give us access to this that we were not able to see before. And this actually is just one piece of our displaced jet trigger program. There are many other subdetectors that are used. So when we put this in combination with all the other triggers that we have, the trigger that I designed is in dark blue here. And you see that it gives us great sensitivity to the sort of mid-lifetime range. But this really complements other triggers that are designed using the tracker all the way out to the muon system. So we have sensitivity for particles decaying between 1 up to 7 meters from our collision point. And this is really nicely highlighted in this paper that came out just earlier this year, showing the performance of our trigger system over the last few years of data taking. Not only do we have sensitivity to this displacement, but we also have sensitivity along a completely different axis. So from our most recent upgrade, we upgraded the Hadron Colorimeter to its readouts being silicon photomultipliers. Silicon photomultipliers are great in terms of their signal-to-noise ratio, but they're also really beneficial because they can give precision timing. So we have precision timing information on the order of a nanosecond, and this information is something I also take advantage of in the displaced and delayed jet trigger. So for a dark sector particle, this may actually arrive at our colorimeter at a delayed time because it may simply be moving relatively slow, and that would give us a delta t between when we'd expect to see a prompt jet and when we'd expect to see a delayed jet. And this is something that we can be highly sensitive to with our trigger system. So again, this is the trigger acceptance versus the timing shift. And this entire blue area, which is for particles arriving at our detector 6 nanoseconds or later than we'd expect for a prompt jet, we have incredible sensitivity to that. This is one of the first uses of this upgraded timing information and has been shown to be quite beneficial, really giving us this sort of extra dimension that we were not able to access before. So this trigger has been implemented for the past few years, and now one of my major projects is diving into the recent data. The trigger is very restrictive in terms of what events it collects. The dedicated trigger that I implemented ends up selecting 1 in 4 million events. However, after collecting data for just 2 years, even with that trigger, we have 90 million events to sort through. And what I'm searching for here is this dark sector model, so Higgs to 2 dark sector particles going back to standard monoparticles. And we expect this to be a relatively rare decay. So we're looking for a really small signal. We might be looking for something like 10 events on top of a huge background. So we need to reduce the number of events that we have by another about 6 orders of magnitude to be sensitive to this potential very small signal. And how I do this is look for variables like the one shown on the left here. So this has the background, which is from data, in black, and you see it's a nice falling spectrum on this variable that's the neutral hadron energy fraction in a jet. This contrasts quite a bit with what we expect from our signal. Our signal is from Monte Carlo simulations, and it's shown in blue. And this displaced jet signal is actually peaked, so this is a really great way to start separating this. So I look at this variable and about 32 other of them, and then use the power of artificial intelligence, particularly with the deep neural network, input all of these variables to that deep neural network, which can output basically a discriminator, a score that can help better separate the signal in the background. And then using that, we have an analysis designed. This is a completely blinded analysis. So we designed the analysis in a control region and a validation region. But the signal region, we're completely blinded to. So hopefully within about a month, I'll be able to open up the box, see what's in the signal region, and see if we have any evidence of the dark sector physics. So throughout the first part of this talk, I really emphasized how the new timing information that we have from our upgrade has been extremely beneficial in terms of the hardware level along with particle triggers, these ongoing Higgs sector searches, and it's been very beneficial for detector performance and detector time alignment. My next project is to use timing information to improve particle identification, and this is a project that I've really been diving into during my first year here at MIT. So when we collide particles, we basically want to use as much information from each of the different subdetector systems that we can in order to determine what came out of the collision. So if we think about the energy measurements in the calorimeter, we also can use information from the tracker to determine if those are spatially linked to charged particle tracks. And that's how we can distinguish, say, electrons and photons, because the photons will be unlinked, they won't have an associated track. We do the similar thing in the Hadron Colorimeter, but what I'd like to emphasize here is that we have timing information, but this is actually not used in our particle identification algorithms. However, that's something that it's quite powerful, and it could bring new techniques to particle reconstruction. So in particular, if we have two jets, two showers of energetic particles that are intersecting our detector, they're going to be depositing energy among many different detector layers. But if we just have access to the energy information, we basically just see this grid of energy information, most of the energy in the center, less at the outside. But it's actually quite difficult to disentangle which jet and which particles those originally came from. However, if we have the timing information, and if these jets were to be arriving at our detector at significantly different times, say 1 nanosecond versus 7 nanoseconds, that's additional information that we could use to start separating. So our algorithm that ends up deciding sort of what particles come from which jets and what particles come from which collisions is particle flow. So currently we have standard particle flow, where we just have access to the energy information. But what I'm adding is timing-aware particle flow, where we basically add this extra dimension, and then we can start to see that this lower corner has particles that are sort of out of time, delayed, and that lets us basically separate the information that they deposit in the detector and more accurately reconstruct the underlying physics that this came from. So my research program really focuses on using low-level detector information to give us a window into new physics, taking multiple forms from improving the triggers, doing improvements in data acquisition and the ongoing search for long-lived particles, as well as improving future particle reconstruction. And all of this is really to come back and answer the central question of what's beyond the standard model and what is the nature of dark matter. So with that, I'd like to say a big thank you to everyone for being here, and in particular, thank you to Neil and Jane for supporting this work and making this possible. So, thank you.
OK, thanks very much. So the floor is open for questions. Sir?
I'll ask a very naive question. We don't know the mass of neutrinos, right?
Right.
How do we know the dark matter is in neutrinos?
Yeah, so we do know a lot about how neutrinos do interact, and in particular for dark matter, we need something to be stable on cosmological scales and give a lot of the observations that we have from early universe measurements and from the galactic measurements. And though neutrinos would be massive, they'd be a fairly light mass and likely not able to give the, because one of the main observations for dark matter is having the extreme gravitational interactions that they can provide in the galaxies. In particular for neutrinos, both they can be light mass, so not give the strongest gravitational interactions that we expect, and we know that they do interact with our detectors and we can be able to observe them. So, and dark matter is basically light, so it does not have those same interactions.
So they weigh small enough that there'd have to be too many of them.
Yeah.
To be dark.
Yeah.
Maybe it's simplest.
Something, yeah.
Krishna?
So thank you for the great talk. So you're using CMS for something it wasn't designed for when it was designed 15 years ago. So if you could completely redesign it from scratch, this is obviously hypothetical, but you're using this detector in a way that goes beyond what it was, how it was intended because of new science questions. So if you wanted to design a detector to go after your science, how would it be different from CMS, or is it perfect?
Yeah, no, that's a great question. And I think this comes up a lot because we're designing detectors and then we're using them for decades. So the ideas that we're trying to search for after that time can definitely evolve. In particular, I think a lot of what CMS is designed for is sort of tracing back to the actual collision point. And I think that's one of the major limitations. So if I could sort of have my perfect detector, it'd be great to have more of this tracking information further out, because the tracks are what give us this like really precise information, and that really helps with our sort of the vertexing pointing back to the collision point. So if we could have more information about particle tracks continuing further out, I think that would help a lot with the displaced jets that we have, because then you'd be able to actually use that precision information instead of just saying, okay, we have a lack of tracking information, what can we do with it? So that would be very beneficial.
What is the main SM background for all this display stuff? And the second one is, how much harder does blinding make your life?
Yeah, great question. So Yeah, so long-lived particle searches are actually pretty unique. I mentioned that we're doing a data-driven background, and this is because it's kind of difficult. A lot of the backgrounds for this are basically in the tails of prompt distributions, and that makes them very difficult to model in Monte Carlo. There are some sources of standard model long-lived particles. There's like the K-long, or if you have a charged pion that was going at a low momentum, that could sort of like take some time spiraling around in our detector before reaching our calorimeters and fake a displaced signature. So we do have some backgrounds like that. But in terms of what we're simulating here, or what we're looking at here, this is purely data-driven background. So we're basically just looking at how much in our control region we can predict sort of what's our fake rate, what's our rate of, does this accidentally look like a long-lived particle, project that to our validation region, and then finally, once we sort of get closure in there, project that all the way to our signal region. So this is difficult because you have to, because it's blinded and like we can't look at the signal region and we're not really confident in our Monte Carlo modeling in the signal region. It does provide some difficulty there because you have to really understand your background validation methods using the data, but it also gives us sort of a benefit that we're purely data-driven. You don't have to worry about what is the discrepancies between data and Monte Carlo.
So in the component you showed inside the detector, what breaks down most often that you need to maintain on PCR? Is it the silicon wafer or the superconducting magnet or what?
Yeah, great question. So currently, the silicon tracker is sort of reaching end of life. Because it's just in the innermost detector, it's going to get the most exposure to radiation damage. So that's what's reaching end of life now, and we're going to have a pretty significant upgrade. We take data through about a month and a half from now, and then we have a long shutdown for 4 years. So we've got pretty significant upgrades to the tracker system. Also, this is showing the barrel version, the barrel section of the detector, but we have 2 end caps on top of this. So I work on the HCal, which is, oops. We go back here. So on the HCal, we also have 2 HCal end caps. And those have also been receiving pretty significant radiation damage. So those ones will also be upgraded during our shutdown period, giving us a huge amount more low-level information, which I'm really excited about because that gives us, it's a high granularity calorimeter that we're replacing this with. So this has an order of magnitude more channels. So the spatial information and the precision timing that we can get out of that will be pretty exciting after the upgrade.
Sabo?
Thank you for the talk. So a few months ago, we had a talk about the years-long investigation about the DAMA signal, the claim of dark matter from the modulation in DAMA. Now, say that when you unblind your boxes, you find something, which of course I wish you to experience. What do you think happens next? Because there is not that many CERN in the world, and so many other places that can reproduce this kind of experiment if you have a positive signal. So what's your view of the next steps?
Yeah, so definitely a great question. So if we were to, say, see something unexpected, something above our background, a signal, first couple of things that we do is, in the same experiment, we'd try and do, okay, does this come from a particle of a given mass? Is there like a mass resonance? And then you could cross-check that with the other general purpose experiment at the LHC, the ATLAS experiment. And beyond that, I think the main direction that this would really help us to go is it would start to give an indication of, okay, here's the particles that we are expecting, that we see this new particle start to couple to, and then probe whatever are there direct detection experiments that could have those same sensitivities. So at least give us like some direction in terms of, okay, if this is a Higgs coupling, let's continue to probe the Higgs in very high precision. If it seems to couple to, I don't know, like B quarks, or if it seems to couple to something else, then that would at least give us a direction to go with the other experiments.
Just one kind of very basic question. You talk about all these events you're saving and all the ones you're throwing out. How many bits of information is an event? And like, what are you actually saving?
Yeah, great question. So let's go. Oh, sorry. So the bits are actually quite restrictive. In terms of bits of the entire event, I don't know if I have a quick answer for that, but I can give an example on the trigger system that I work on. So we're recording energy information. We have about 12 bits to do so of that per cell. We have 6 bits of timing information. So that gives us half nanosecond resolution. Even in terms of the timing information that we can end up using at the trigger system before we've made that decision, we have to reduce those 6 bits to 2 bits of information. And then we have to combine, so then we sort of have these, like, we only have a couple of pieces of information about, do we have prompt particles, delayed particles, highly delayed particles. And then in the trigger system, we end up basically doing this sort of reduction multiple times. We end up with a single bit per jet that indicates yes or no, this looks like a displaced jet. So we've done this like huge data compression already there. So this is what's done in every single trigger effectively. It's going from this massive amount of information to try and condense it in the most sort of informed way that you can to process that offline.
Okay, sorry, yes, go ahead.
Really quickly, can you tell us the silicon, where it comes from? I think it comes from Finland, micronova, and it is producing very high purity plates. Can you tell us a little bit more about that?
For the silicon tracker, I don't actually know where that's produced from. That's a great question.
It is, I know because I'm from Finland.
Okay.
It's producing micronova, which
Okay.
is UNESCO, and the group in Helsinki
Mhm.
is the one producing also UT University, which have been on
Yeah.
So it's a very important component, and as you say, I guess that it will be 2 years of pause in order to put together everything.
Yeah, like huge effort in terms of characterizing the new ones, characterizing the modules, making sure it's low noise, et cetera, as you say. Yeah.
Gillian, I'm going to use the last 30 seconds to ask you a question myself.
Please do.
What's the connection between displaced jets and delayed jets? I mean, aren't displaced jets displaced because you have to wait for the dark matter particles to propagate? So then wouldn't they be delayed also?
Yeah, so it really depends. They can come hand in hand, because you could have sort of a highly relativistic particle, and then the displacement would not give you a high delay. So you could have the displacement without the delay, or even if the particle was sort of like very heavy and didn't move very far, you could have a high delay without a high displacement. So you sort of have this whole phase space of highly displaced, highly delayed,
So
or
it's
some
two different
fraction.
ways of looking at it.
Yeah, exactly.
Yeah.
So because at the trigger we're actually sensitive to both of those, that gives us more sensitivity to the whole range. So at different mass models, one is maybe more powerful than the other.
Thanks very much. Okay, we are out of time here, so let's thank Gillian again.
All right, thank you.